Hi, y'all, and we're back for another round of physics. And today, we're going to move on from the 1D motion and start considering the idea of 2D or maybe even 3D motion. So we are scaling it up to more difficult situations. But I say, don't be too concerned. Remember, I said if you know how to deal with 1D motion, then you already know how to deal with 2D or 3D motion. For example, 2D motion is two 1D motion problems, or 3D motion can get turned into three 1D motion problems. So if you have the basic understandings from the last several lectures or the last several videos, then I would argue most of the stuff that you know you've already seen here. That being said, before we actually get into this, I would like to go back and talk a little bit about vectors. Now, I'm not going to actually do the algebraic or the geometric definitions, or from the mathematical standpoint. I'm not interested in that now. I assume that you know it. What I really want to be thinking about or talking about are some of the physical vectors that we've actually started using in this class, although we haven't explicitly said anything about it. So the first one that I want to point out is what I will call the position vector. So I'll put position vector. And I'm going to I'll try to be consistent in my video lectures here. But the position vector, I tend to use the variable r. And I believe that your book also does this. Okay? And what this is it's the vector, I'll say vector pointing from the origin, so I'll put from origin to location in space, or to the object. Okay. Hence the position vector. If you want to indicate the position of an object, that would be the vector pointing from the origin to the object's location. Now there's one thing, or at least one thing, that I really need to highlight, and that is the origin. In order to have an origin, you must have a coordinate axis. In other words, if you want to create position vectors, you first have to specify where the origin is, which means you have to draw out your axes. Okay? Now, I will say again, your choice of axes should not affect the physics. You have 100% flexibility in choosing a coordinate system and where you want to put your origin and how you want to have your axes oriented. Choose the orientation that makes your life the easiest. With great power comes great responsibility. A good choice of axes will make your life easy. A bad choice could make it impossible to actually finish the problem. Okay? So that's something that sometimes it takes a little bit. Sometimes you're going to choose an axis, you'll get stuck, you'll say, maybe that wasn't the best choice, and you'll choose something else. That's perfectly fine. Okay? Just be aware that that's something that sometimes you have to actually do. Okay, so that being said, the origin to the object. Okay, that's the position vector. Now the next one that we've dealt with is what I refer to as the displacement vector. And if we're talking about finite time intervals, I'll use delta r, so the change in the position vector. Or if you're talking about instantaneous displacements, then we would actually use dr, so the derivative form. These are synonymous. It just deals with, are you dealing with a finite time interval, 1 second, half a second, a tenth of a second, etc., or are you dealing with truly instantaneous, 1 moment in time and the next moment in time? Okay, so there's those. How I would say this is, of course, you're already familiar with delta notation. You know that this stands for the change in. And I will say this is vector representing the change in object's location. Change in object's location. Okay. That's kind of boring. What I will highlight here is notice that you're dealing with one object at two different times. Okay, let me underline that. Okay, one object at two different times. In fact, I'll double underline it. And you'll see why in a second. I'm going to give you another vector which we have not seen, but that will be very important in future chapters. I just thought it might be a good idea to put it in here. So you have the position vector. Excuse me, I wanted black. You have the position vector, 1. You have the displacement vector, 2. Okay. Now, one of the cool things, and I'll take a byline about the displacement vector, one of the cool things about the displacement vector is that it does not depend on your choice of origin. Okay? I'll say that again. It does not depend on your choice in origin. That's really cool. Okay? I said earlier, you have the ability to put your origin and orient your axes however you want it to. Choose the orientation and the location that makes your life easy. The other issue is that your choice of origin does not affect the physics. It doesn't matter if I put my origin right here or if I move it over here. Okay? I should get the same physics going on. And that, I mean, as the heuristic argument, let me say I put my origin here and I have my pen here. What happens if I let go of the pen? It still falls. And of course, if I move my origin, say from this location to this location, right in front of my face, what happens when I let go of the pen? It still falls. And that's what I mean by your location of the origin should not affect the physics. The pen still falls regardless of where I decide to put my axes. Okay. We could actually see that if we want. Let's go ahead and get rid of that. So let's go ahead and clear out our screen here. Okay. And we can see that if we want. Let's say, for example, yes, lines, excuse me. Let's say, for example, I choose to put my origin here. Call this my X. I'll call this my Y. And let's say my object is right here at time, the first time. Put it T naught. And it's here at T final. Okay. Now, of course, I need to draw in my position vectors. I will call this, let me get some lines here that'll make it easier. I will call this my initial, and let me choose a different, here's my final. There's my final position vector. Okay. So this is our final, my final position vector. This is our initial, my initial position vector. And now remember that when we have a change in R, that change in symbol means that it's our final minus our initial. Okay. Well, let's go ahead for good practice. Let's go ahead and actually do those two calculations. Final, okay, well, here's my final. Okay. I take my initial and I've got the negative sign, which means that flips the direction of my initial. So let's see if I can actually highlight this. Okay. So there's my initial, and I apologize, we'll have to get rid of the other piece, but we'll flip it 180 degrees. Did I get that? 180? Good. I've got 180 degrees. Let me go ahead and get rid of some of this other gack. So now I've got my R initial, and I've got the negative sign taken care of. That rotates at 180 degrees. And now I just simply need to do the tip to tail method. So let me take this, and we're going to move it to the tip of the final. Okay, see that? Good. And then lastly, we draw from the empty tail to the empty tip. This is my delta r. There's my delta r. Okay, good so far? And remember, I could actually translate that. We could translate that to up here as well. Here's my delta r. Delta r. Good. Now let's say, for example, let's get rid of all this rigmarole. So I'm going to fast forward the video here. So let me go ahead and choose a second set of axes, and I am going to make it dramatically different than the location of my first. So I think that without a doubt, we would argue that this is definitely a different axis. Now again, we'll stretch a line. Here we go. Here is the initial. Notice I haven't changed the location of my object. I've just moved where my axis is. Let's say here's my final. And again, I'm just using the same colors. And again, our final, our not. And again, what I want to do is our final minus our not. So let's go ahead and get a copy of my initial position vector. Copy, paste. We will rotate it 180 degrees. Good. And let me get rid of this rigmarole gack that we really don't care about. Right, I'll get rid of that. Okay. Just to clean it up a bit. Good. Now we will translate it. We'll apply the tip to tail method. So I've placed the tip, the tail of my initial on the tip of my final. There we go. And we see that if you'll cross your eyes just a little bit, because I'm doing this freehand, we see that again, we end up with a final change in position, delta r, which is exactly the same as what we got for the previous axes choice. And this should make some intuitive sense as well. I didn't change anything about the object, so the displacement of the object shouldn't change. Okay, so that's just algebraically going, or I wanted to go through and show you that, yeah, graphically, it doesn't matter where I put the axes. I end up with the same displacement vector. Okay, good. Let's go ahead and clear the table here. It's always good to pick up after yourself after you're done. Good. Okay. So that being said, of course, you already know that there's another vector, very important in physics, that depends on the displacement vector. The velocity. So velocity vector v, which if you're dealing with finite time intervals, we would write as this. T. 1 second strobe flashes, half a second strobe flashes. Or if you want the instantaneous, we'll write it like this in terms of derivatives. Either way, though, if delta r or correspondingly dr, if these are independent, put indep of axes location, if these are independent of axis location, then your velocity will similarly be independent of your axis locations, which is really nice. Again, the choice of axes should not affect the physics. You could go, but wait, there's more. I feel like a car salesman, but wait, of course, your acceleration is also a vector, a. For finite time intervals, we have delta v over delta t. For instantaneous or really small time intervals, we use the derivative notation. And again, if the velocity is independent of the coordinate axes, this or this, that means your acceleration is independent of your coordinate axes. So everything falls together. Your displacement vector, your velocity vector, your acceleration vector, those are all independent of your coordinate axes. Your position vector is not. That definitely depends on where your origin is or where you put your axes. Okay. So as promised, there's one more vector that I will give you right now, and we'll see this in future chapters. Namely, it'll first come into play when we're dealing with gravity, the universal law of gravity, but I want to give it to you now since we're talking about different types of vectors. So put it in your memory bank, it will come back later. And that is what I call the relative position vector. Okay. And generally how I will represent this is with an R. Okay, so it looks like the position vector. And then down, I usually put subscripts. I'll put like a 1 and a 2. Object 1, object 2. Okay. What is this? This is the vector which points from object 1 to object 2. Okay. Or if I can summarize it differently, I can say two objects at a single time. Note how this is slightly different than the displacement vector. The displacement vector is one object at 2 times. The relative position vector is 2 objects at 1 time. Okay? So pause that, hack through that again. 2 objects at 1 time as compared to 1 object at 2 times. Okay? Now how you get the relative position vector? Well, if you're given 2 objects, so let's go ahead and draw in my coordinate axes. It's always good to have a coordinate axis. Here's object 1. We'll say here's object 2. Okay. You have the position vector of object 1. That's from the origin to object 1. Always forget about that. Oops. To object 1, which I will call R1. You have a second vector, second position vector, which goes from the origin to the second object, which we will call R2. Okay. And if it points from 1, so this would be the initial location, to object 2, and I'll call object 2 the final, okay, that means I should have something that points in this direction. This would be the relative position vector R12. You say, how can I do that algebraically? Say R12, it points to object 2, the location of object 2, from the location of object 1. Okay. So I kind of think of this as final minus initial still. Okay. It's pointing from 1 to 2. So the final is 2, the initial is 1. I do that subtraction. Okay. So, like I said, this will mainly, we'll first see this for universal gravity. But then it'll come up again in Coulomb's law. It'll come back again in Biot-Savart. Okay, so I'm just introducing it now. We won't use it for a couple of chapters, but please know that it's in the cards. Good? Cool. Well, I think, let me see here. Yeah, I think that this might be a good place to stop for right now. The next video will just introduce 2D motion and bringing back in this vector, these ideas of vectors. So I will leave it there for right now, and I'll see you next time. Thanks for your attention.